Hello and welcome again. In this section, we are going to review the concepts related to interaction of radiation with matter. Once radiation is emitted by atoms and nuclei, it travels in the empty space, which is in between atoms, but is subject to interactions with the material surrounding the atoms where it comes from. Now, during these interactions, energy is deposited, and this deposition of energy may be the source for the radiation damage. Again, also for this chapter, the content of the chapter is not covered in detail here. It is covered much more in details in other courses, and specifically any textbook related to radiation physics will treat in much deeper detail than we do here the mechanisms of interaction between radiation and matter. For us as inspectors, it's important to remember a few important concepts, but during this training course we are just going to review them quickly. If you reference the textbook, which is very popular in the UAE, Atoms, Radiation and Radiation Protection by James Turner. In that textbook, in the chapter 5, interaction of heavy charged particles with matter is treated, and in chapter 6, the interaction of electrons with matter is treated. And there are some additional 2 chapters. One is called Phenomena Associated with Charged Particle Tracks, and the last one is Interaction of Photons with Matter. Of course, neutron interaction is very important, although neutron interaction is more complex and requires different mathematical calculations in order to be described fully. The interaction of neutrons with matter is also very important for shielding purposes and for understanding the mechanisms which underlie deposition of energy from neutrons. I have to stress that anything which has to do with neutrons is more complicated than other radiation. So, for example, in some textbooks there are specific chapters devoted to the treatment of the interaction of neutrons with matter and the slowing down of neutrons. There is an enormous experience in studying populations of neutrons, their evolution and their fate in a nuclear reactor. So a considerable complex physics, mathematics, and a number of codes and software have been developed for neutron calculations within the reactor core. But now, let's move forward. The chapter is devoted to interaction of radiation with matter. If you feel comfortable with this material, you can skip this presentation altogether. This presentation is just a review. This section is about the interaction of radiation with matter. This is a very important topic for 2 main reasons. The first, describing how radiation interacts with materials, surrounding materials, is a way of describing the ability of materials to shield or stop radiation. Secondly, and most important, being able to describe the mechanisms of energy deposition is very important because it allows us to describe how damage is created in materials, and more specifically, biological damage. We are, in radiological protection, interested mainly at biological damage, so understanding how radiation deposits energy and creates damage in cells and then in tissues and organs and organisms is one of the final and most important purposes of our study. Now, it's always very important to remember that each radiation has a very different mechanism of interaction with materials. And we will delve a little bit more into this subject, although this chapter is a review chapter. We will not go in a very specific detail of the mathematics and physics behind these concepts. We will start by looking at this table, which indicates for radiation emissions typical energies at which these are emitted and typical ranges, that is, path that radiation can travel both in air and in water. Now, water, let me just remind you, is a very good approximation of the characteristic of human body. So very frequently, attenuation or slowing down in water is considered as an equivalent of the interaction with the human body. So if you consider, for example, alpha particles, which is the first row, we know that alpha particles have a charge. They carry two electric charges, and the energies, you remember from the previous chapter, normally in a radioactive decay, an alpha particle will carry energies of the order of mega electron volt. Now, as indicated here, in most cases, alpha particles are emitted with energies of 3 to 10 mega electron volt. Now, these particles, which are quite energetic, travel in air a few centimeters. Here it's indicated as a range, as an interval, as a bracket, 2 to 10 centimeters. And in water, the range is much smaller, just a few tenths or hundreds of micrometers. So the ability of alpha particles to penetrate materials is very, very limited. Let's have a look at betas, and for the purpose of this study, beta plus or beta minus, it's the same behavior in matter. Now, beta particles, they carry one electric charge. During radioactive decays, they normally are emitted with energies of fractions of mega electron volt or some mega electron volt. It's very rare. For example, one notable case is strontium-90, yttrium-90 emission, beta emission, which has an energy, a beta energy of some mega electron volt. Now, it's quite rare that betas are emitted with energy exceeding a few mega electron volt. They travel a few meters in air and less than a centimeter in water. Now, already looking at these two lines, two rows, we understand that there is a huge difference in the mechanism of interaction between alpha particles and beta particles. Because in the first case, we have higher energies, but very, very small paths. And in the second case, we have energies which are lower than the average energy of an alpha particle, but paths which are much longer than the alpha particles in air and in water. This is already a clear indication that it's not only the energy which determines the kind and depth of interaction, but there are other parameters, and indeed it's the charge, it is the mass, it is also the type of interaction that particles undergo with materials. Now, the other three radiation here, neutrons and photons in terms of X-rays and gamma rays, they are, of course, uncharged radiation, so they don't bear any charge. Neutrons can be emitted with a very wide range of energies, ranging from a few mega electron volt, even more in big accelerators or in galactic radiation, down to milli electron volt or even much less. So they span several decades of energy. It's very difficult to just give an indication of one parameter, so the range is quite large. As you can read here, in air, they can travel meters, 100 meters even, and in water, they travel, yes, but much less again, and the distance they travel is a few tenths of centimeters up to a meter. X-rays and gamma rays, they are photons of the same nature, and normally, as we have discussed, their energy ranges are different because X-rays are emitted from the atom and gamma rays are emitted from the nucleus. So normally the former have lower energies, and normally the latter have higher energies ranges, but this is not always true. As an indication, here, X-rays, they are emitted with energies of the order of the kilo-electron volt or tens of kilo-electron volt. They can travel in air meters and in water millimeters or centimeters. While gamma rays, being more energetic, up to normally a few mega-electron volt, they travel centimeters or even meters, tens of meters in air, and they travel millimeters or tens of centimeters in water. So in the case of photons, as you can see, as both X-rays and gamma rays have the same physical properties, and the only difference, at least in this analysis, is their energy, the energy is impacting heavily on the abilities of photons to penetrate materials. For neutrons, as we will see, the interaction is very different, but a final conclusion from this table is, first of all, different radiation have very different penetration depths into materials, depending on their nature and not only their energy. Plus, we also need to add that the mechanisms of interaction of charged particles are very different from the mechanisms of interactions of photons on one hand and neutrons, but both photons and neutrons are uncharged particles. Let's start this review by looking at the interaction of alpha particles with materials. So alpha particle, we know they are an aggregate which is made of 2 protons and 2 neutrons, and normally at the energies of radioactive decays they don't carry electrons. It's not a nucleus, it's an ion, it's an aggregate which is ionized and has a charge of +2 electric charges. Alpha particles, we have discussed already several times, their kinetic energy is on the order of a few mega-electron volt, 5, 6, 8 mega-electron volt. So this is the typical range. And what happens when an alpha particle is emitted? The energy of the decay is shared between alpha particle and the recoil nucleus, which is the product of this transformation. Very important, as we have seen in one of the exercises, the recoil nucleus, which is also ionized and much heavier than the alpha particle, brings in this recoil a significant fraction of the energy, which cannot be neglected in terms of radiation damage. Of course, at the end of their path, alpha particles will slow down and stop eventually, picking up 2 electrons from the surrounding materials and becoming a neutral helium atom. Now, the mechanism of interaction of alpha particles is basically an electric interaction, a Coulombian process from Coulomb, the attraction or repulsion of 2 electric charges. It is a continuous process, and this process allows for the alpha particle to lose gradually its energy along a very, very short path, which is linear, straight, and very, very short. Now this is, as we will see, very different from the mechanism of interaction of betas in matter, for example. Here we have quite an interesting graph which depicts the number of ionization pairs, so the number of pairs of electrons and ionized atoms which are created by the passage of an alpha particle in a material. So you read this graph by imagining that there is a source positioned here at the origin, emitting towards the x-axis. And for example, let's take the first curve. the number of pairs which are created increases from 4,000 pairs per millimeter, increases with increasing depth in this material, the material is air, up to a peak where the ionization pair number is maximum, and by the way, it almost doubles in this example, and then falls abruptly to zero, which means that from this point onwards, not only the number of pairs which are created are much less, but this means that the particle is not moving anymore. The alpha particle is coming to a stop at this distance, 4 centimeters in air, for the emission of polonium-210. Now, this emission has an energy of around 5 megaelectron-volt, and you can compare this behavior, which is very similar in structure, with the one of polonium-214. Here the energy is of the order of 7.7 megaelectron-volt. In both cases, this peak of ionization happens at a certain depth, and this peak is called Bragg peak. Interestingly, in both cases, after the Bragg's peak, the particle comes to a stop. Now, this is what we call range. In the case of alpha particles, the range is defined as the maximum distance an alpha particle can travel in a specific material. So, as you can see here, I imagined it like a wall. The first particle from the emission of polonium-210 cannot travel over, let's say, 4 centimeters in air. And the second particle of polonium-214 cannot travel beyond 7 centimeters in air. Now, not by chance, this example has been chosen because, as you will see, there is a very simple, clear rule of thumb which allows you to remember what is the distance, the range of an alpha particle in air. And we will see that later. I can already anticipate. The range in air of an alpha particle of an energy x megaelectron-volt is around x centimeters. So, as we can see, around 7-8 centimeters for this emission, around 5-4 centimeters for this second emission. Now, if we look a little bit more in detail to the alpha particle interaction and the range concept, we need to remember that alpha particles are emitted basically monoenergetically. This is because the alpha decay is a two-body process. There is a statistical distribution over the energy of emission of an alpha particle. But as we have seen in one of the exercises, we can calculate the energy at which an alpha particle is emitted by using classical mechanics splitting over the mass of the recoiling nucleus and the alpha particle, the original Q value of the reaction. So this means that the range of an alpha particle depends on the energy and is indicated normally as the centimeters of air corresponding to the path of the alpha particle, which is roughly, as we said, the energy in megaelectron-volt of that alpha particles. The value of the range that you can see here, so this R is the theoretical range. In reality, the range is a little bit more, and this is due to the fact that alpha particles having this distribution of energy, they also have a distribution of ranges. This is called straggling. It's possible to extrapolate and also to have a correlation between the expected value of the range and the energy of the alpha particle. And if you need to calculate it, this is one of several correlations, but a very simple one which allows to determine the range by knowing the energy of the alpha particle. Just a few words related to recoil nuclei. So recoil nuclei, as we have described, happen whenever there is an alpha decay But a very special case of nuclei recoiling is fission. You may remember that during fission, a larger nuclide is split into two fragments. These fragments are very big as well. Now, it's quite interesting to have a look at some numbers there, because during the fission reaction in uranium, around 170 mega electron volt of energy are shared by the two recoiling nuclei. We can say that this is around 70 mega electron volt of kinetic energy to a smaller fragment, and around 100 mega electron volt to a heavier one. Now, in the balance, you also remember that there is additional energy being emitted in terms of radioactive decays, including also delayed neutrons and beta emissions. But in terms of the kinetic energy of the two fragments, it's quite a huge amount of energy, 170 mega electron volt, split into the two recoiling nuclei, which, by the way, are heavily ionized. They have charges of around plus 20, so they interact very strongly with the material. They deposit all this energy in a very, very short path, and this brings the temperature up very much because a considerable heat is dissipated in this process. Now, this is the reason why the fuel elements they raise their temperature so much after several fission reactions took place, mainly due to this kind of interactions of very, very heavy fragments with the surrounding matrix, the surrounding material. Now, important points. As you can see, this is just a qualitative treatment of radiation interaction. But there are a few important points to remember here. So the first one is alpha particles ranges are very small. Therefore, it's very simple, it's very easy to shield alpha particles effectively. You may remember that just a few centimeters of air represent a range, even for the more energetic alpha particles. Just a few millimeters, sometimes less, micrometers of water can stop alpha particles. And we demonstrate very often in these experimentations that a sheet of paper is enough to stop alpha particles. Indeed, alpha particles are also stopped by the layer, the 70 micrometers layer of dead skin we have all around our body. So from the point of view of shielding, alpha particles, they can be shielded very easily, but it's most important to remember that their ionization power is very high, very big. Therefore, the energy that alpha particles deliver during their tracks is very high and can create an important damage and an important biological damage as well. Therefore, alpha particles are not a big concerns in terms of external exposure to the body, but if an alpha emitter is inhaled or ingested and enters the human body, it can deliver very high doses. It can deliver a lot of energy locally due to the fact that it is not shielded anymore by the external skin. Localized doses, as I write here, can be very high, and this is the reason why it's very important to protect workers and inspectors' breathing apparatuses whenever there is an alpha radiation risk. So, alpha emitters, not dangerous for external exposure, but potentially very dangerous for internal exposure due to either inhalation or ingestions of alpha-emitting radionuclides. The mechanism of interaction of beta particles with materials is completely different from the alpha particles. Well, first of all, beta particles are electrons, high-velocity electrons, which are called beta particles just because they originate in the nucleus, but they are absolutely the same particle as the electrons orbiting around other atoms. Therefore, the interaction of electrons with other electrons is an interaction of the same particle with the same charge, with the same mass, while we should remember the alpha particle has an energy, a mass of 4,000 megaelectron volt, and is interacting, as we said, mainly with electrons which are loosely bound in atoms. This is not the case for beta particles. Beta particles, they go and interact with electrons which are exactly the same mass, and also same size, same dimensions. The energy of a beta particle depends on its velocity, and the opposite also is true. And beta particles with energies of some megaelectron volt or in that range can have velocities that approach the speed of light, so they have relativistic behavior and relativistic interactions with materials. From the point of view of the phenomenology, beta particles, when they interact with materials, they can bounce back. They have very strong scattering at very sharp angles, just because they have the same mass and the same charge of the particles they are mainly interacting with. During their path, beta particles lose energy in each dramatic interaction with another electron, basically with 4 different mechanisms. One is direct ionization, which means the beta particle is going to ionize, to strip one electron from a surrounding atom, an atom in the surroundings, by creation of delta rays. Delta rays are secondary electrons which are created by the interaction of beta particles with a material, who are themselves able to ionize. So they create secondary tracks in materials. The original track, we will see an example later, of the beta particle in the material, plus additional tracks generated by the secondary energetic delta rays. As they move very fast with energies which allow them to approach the speed of light, there are also 2 additional important mechanisms of energy loss. One is bremsstrahlung radiation, so emissions of photons. You remember we described this effect before. The emission of energy in form of radiant energy due to the deceleration or acceleration of a charged particle. And a very specific mechanism of interaction, the creation of Cherenkov radiation. This is specifically possible for beta particles of high velocity, of high energy, in a medium in which the particle can exceed the speed of light in that specific medium, so specifically in water normally. From the point of view of the description of these effects, ionization is the ability to remove, to strip an electron from an atom, and the beta particle, whether positive or negative, behaves the same way, either by pushing or pulling, by an attraction or a repulsion towards another electron in the atom. This is the reason why the path of a beta particle is, or could be, very complex and tortuous, full of bends and curves, because each interaction is quite dramatic for the beta particles who interacts with another particle of same mass and charge. So in this graph, we have the path of a beta emission. So this beta emission has been originated, for example, here, and you see it has followed a path which is quite complex with a lot of changes in direction, and at some point even has bounced almost back, and then again it has been bounced with very sharp angle, and eventually the particle has been has slowed down and has been absorbed. Now, what we want to show here is the creation of secondary particles, and we will see a zoom of this part on the right of this picture. So during the track, the beta particle can create additional secondary electrons, and these secondary electrons may have enough energy to ionize themselves along their own tracks other atoms. This is a very efficient way of dissipating energy, and it is indeed quite an important mechanism for beta particles. Now, what we indicate here is that these secondary ionized electrons should have an energy above 1 electron volt or a bit more in order to be able themselves to ionize other particles, other atoms, and they are called, in this case, they are called delta rays. Now, the generation of photon radiation due to the deceleration or acceleration of charged particles is something we have already introduced before, and normally is indicated with the German word bremsstrahlung, braking radiation. Now, braking radiation should sound familiar for you because it is the mechanism by which X-rays are created in X-ray machines. We have a very energetic, very fast electron, which is sent to interact with the target, and in this interaction it slows down very quickly and generates an emission, a photon emission of X-rays. The emission of bremsstrahlung radiation for beta particles is the result of the interaction between the beta particle, the electron, and a nucleus of an atom close to which the beta particle is passing by. There is an attractive force which deflects the electron, the beta particle, in its path, and this deflection is a deceleration, and therefore energy is dissipated by radiating X-rays, and this is a significant mechanism of loss of energy by beta particles. This effect is more frequent in materials which are very massive, having a high Z, and this can be easily also understood. Now, this is a visual representation of the path of the electron, of the beta particle, attracted by the nucleus, deflecting its path from an original vector in this direction to a final vector in this direction. And during this deflection, one or more photons of X-rays are emitted, and the energy of those photons is the energy difference between the original state and the final state of the electron. Bremsstrahlung can account for as much as 10% of the energy loss of 2 megaelectron-volt beta particles in heavy elements. So it is quite a significant effect for shielding materials, for very heavy shielding materials. But in lower hydrogenated material, like in tissue, for example, the emission of X-rays represents less than 1% of the energy loss of beta particles. So this is quite significant. It means that this is not an important mechanism of interaction when a beta particle is interacting with water or water-like tissues. Some final remarks on the beta interaction. Well, the first remark is interaction by bremsstrahlung is still today the way X-rays are generated for industrial or medical purposes, because it's a very effective way of converting the kinetic energy of an electron into radiating energy of a photon. Another important observation is beta sources should be shielded and housed not in heavy materials, not in high Z materials, because If the beta particle interacts with high Z material, this can generate X-rays. And this will create an additional dose instead of shielding that emission. So you will notice that normally beta sources are shielded in plastic containers because plastic containers can effectively slow down electrons and reduce very much the bremsstrahlung because their Z is normally very, very small. A last important observation is the fact that the range concept for beta particles doesn't have really very much sense. Due to the fact that the path is so complex in materials, to know that the path traveled was, say, 10 centimeters doesn't really help us to understand how deep beta particles can go into a material, because that path can be also very long, but the penetration may be much, much smaller than what indicated by the path itself. Why all this is important? Well, it's important because all the radiation protection instrumentation, they respond differently depending on the radiation, depending on its energy, and they need to be calibrated in the practice by using radiation standards which are as close as possible to the radiation that one wants to measure. And normally, radiation protection instruments, beta sensitive, are calibrated by using standards either of strontium-90, carbon-14, technetium, lead, promethium, and normally these standards, they are very well defined. This is a leaflet from beta particle standards from a commercial manufacturer. So a lot of information, dimensions, thicknesses, energy of the emission are very well known. But if we remember that a beta emission is indeed quite a complex mix of different energies, we also understand how important it is the knowledge of the radionuclide that one wants to measure. You will hear many times in radiation protection the wording, the nuclide vector, or the source term. Now, these wordings, they indicate it is very important to have a knowledge of the radionuclides that in the practice are the emitters that you want to measure, for several reasons. One, the appropriate calibration can be used. So you will use an instrument sensitive to beta radiation with an appropriate beta calibration. But more importantly, even the appropriate energy and appropriate corrective factors can be applied whenever we have knowledge that the emission is of a specific kind and not of a different one. The difference in the measurement can be significant specifically depending if the beta emitter is a high energy beta emitter or if it is a low energy or a pure beta emitter. In the practice, this is not possible. In most cases, in the majority of cases, when we go and measure radiation, we don't have an a priori knowledge of radiation in that environment. So what radiation protection technicians do is they do an educated guess. They choose by checking the radionuclides present in that environment. They choose an energy which is an appropriate average or an appropriate guess of what they will need to measure. But normally, one single measurement is not enough to give a thorough understanding of the radiation, the activity or the contamination in a specific radiation field. Before we go to the photons interaction, just one last word related to the Cherenkov radiation. Cherenkov radiation is not a very significant interaction mechanism for betas, but it's a very peculiar one because it is accompanied by a specific blue light which is seen only in very high activity beta sources under meters of water, shielded, for example, in industrial irradiators, or in the ponds of nuclear reactors, when highly active fuel assemblies are moved from the reactor core to the pond for cool down and temporary storage. Now, there are many of very energetic beta emitters, so a lot of high energetic beta particles will enter the water of the pond with a velocity which is even higher than the velocity of light, than the speed of light in the water, creating a sort of interference. So there is the creation of this glow, this blue glow, which is typical of the Cherenkov radiation. In this picture that I took in 2013 during a visit to an industrial irradiator, you can see the pool, the storage pool of the facility containing several irradiation pencils. Those are those racks, vertical racks that you see on the right towards the wall of the pool. And these are pencils like 50 or 60 centimeters long, and there are a few hundreds of these pencils. Now, the total activity here, it's quite staggering. It was around 50 million curies. Here it's very hard to use the becquerel. You remember that a becquerel is, a curie is 3.7 10 to the 10th becquerel. So we are talking here 50 millions, 5 to the power of 7 multiplied 3.7 10 to the power of 10. So quite a huge value of activity. Cobalt-60 is a gamma emitter, emitting 2 gamma rays, energetic, more than 1 mega electron volt, but it's also a beta emitter. And this beta emission, as you can see, is creating this blue glow in the pool. And this is exactly Cherenkov radiation. Let's go now to photons interactions. We have seen alphas and betas, charged particles. They interact directly with either electrons or nuclei via Coulombian interaction. Now, for photons, the mechanism is completely different because photons, they don't carry a charge. So the way they slow down is basically nothing happens between one interaction and the next one. And each interaction is a dramatic event for the photon, in which most probably will lose part of its energy by some of the mechanisms we are going to discuss now. And they all involve the creation of secondary particles. So, important to remember, while charged particles slow down by interacting with atoms and electrons and creating ionization directly in the material, non-directly ionizing radiation like photons, but we will see similarly also with neutrons, they interact with the atom, generating secondary particles, which are electrons, which in turn they slow down by the same mechanisms of beta particles. So the difference here is in between one interaction and the next one, the photon doesn't slow down, it doesn't change direction, it doesn't lose energy, it just travels in the material. When an interaction takes place, a photon interacts by photoelectric effect, by Compton scattering, or by pair creation. These are the three most important interactions between photons and materials. Photoelectric means that the photon is actually stripping an electron from the atom. Compton scattering means that the photon is deflected, and in this deflection loses part of its energy and gives this difference between the original kinetic energy and the final kinetic energy to the electron, the Compton electron, which is generated in this interaction. And the third one, pair creation, is a little bit more complex and involves the creation of a pair of electron and anti-electron, a positron, and the disappearance of the photon. We will see this a little bit in detail. There are also other mechanisms of interaction, but they are not so important for radiation protection applications. It's very important, as I mentioned before, the photon travels without any disturbance from one interaction site to the next interaction site. Nothing happens in between. It doesn't change any parameter, velocity, direction. Nothing changes. So, big differences between photons and charged particles. Charged particles can be stopped completely, while photons, they are not stopped because they don't lose progressively their energy. They are just attenuated progressively, and at some point, by a very thick absorber, the number of photons will decrease down to a certain threshold. But it's very difficult to bring to zero the actual photons which are emitted by a source. Second, charged particles slow down gradually by having continuous interactions with different atoms. Imagine an alpha particle or a beta particle travels in a material which is a sea of electrons and atoms. So there is a continuous interaction, not only with the closest atom, although it will be the stronger interaction, but also with others in the surroundings. So it is a continuous slowing down, while for photons, as mentioned, this is not the case. Their single, isolated interactions are dramatic moments in which they lose large fractions of their energy globally in a limited number of events. So the way the attenuation of photons is described in the practice, in operational practice, is by using this kind of curves. These are attenuation curves in terms of energy, the energy here in megaelectron volt, and in terms of different materials. So for example, for lead, if you follow this curve, the attenuation is very high for lower energies. Then there is a specific steep step, and then again it goes down, and eventually it will pick up a little bit more for very high energies. And the similar behavior is true for other absorbers, although you have to consider that these graphs are logarithmic ones, so the change are significant, although they don't look like so much in the picture. So these kind of curves are generated, and they help us to understand the interaction between beams of photons and specific materials. Now, how are they generated themselves? They are generated by interposing absorbers between a gamma emitter and a detector positioned in good geometry. Now, good geometry is very important, especially for the cases which are not good geometry, which is the majority of cases in reality. So the good geometry is a condition which can be obtained in a laboratory in which a source emitting photons in 4 pi, so in every direction, is appropriately collimated. Therefore, only those photons who are directed towards the axis can exit. They are attenuated by a specific attenuator, and as a result, they are also a little bit scattered. But again, with a second collimator, we are going just to pick those who kept the same direction and then count them in the detector. This is an ideal condition. It's called good geometry and allows to create those theoretical attenuation curves which have this typical behavior of a decreasing exponential. This is an ideal situation which depicts the attenuation of gamma rays in a laboratory condition, and as this is a statistical phenomenon, the decrease in the number of radiation detected, or if you want here the ratio between the original number and the number at a certain thickness T, depends exponentially from the thickness of the absorber by using a parameter which is indicated here as mu. This mu is called the attenuation coefficient. And the attenuation coefficient is quite important. It's a parameter which is stated for different materials and takes into account the photoelectric effect, the Compton scattering, and the creation of pairs, the pair creation. This mu is indicated as linear attenuation coefficient, and there is a second attenuation coefficient that we will see a little bit later. So just to wrap up here, the intensity of a beam in a condition of good geometry is the original intensity of the beam multiplied by a decreasing exponential, which is a function of the thickness of the absorber and the function of the material of the absorber. This linear attenuation coefficient depends from the energy of the beam, but depends also from the material we are looking at. Now, importantly, as I said before, good geometry basically never happens in reality because we don't have two well-oriented collimators in order to select only the photons of a specific direction before measuring them. Those are laboratory conditions. In the practice, what happens is there is no collimation at all. Gamma rays are emitted in every direction, so they are also deflected from every direction, and original gamma rays in a direction which was not in the detector may be deflected again towards the detector. This effect is called build-up. Build-up at the same time changes those rates because it brings photons which were not originally due to reach the detector or the point, brings those photons back to the point of interest, and at the same time changes the quality of the beam. Because if the beam has a specific energy at the beginning, those photons who have been deflected have lost energy, so they have a lower energy, and they are deflected again and then brought to the point of interest. So the beam, which we can imagine was monoenergetic at the beginning, is no more monoenergetic. It has been degraded by the effect of the build-up. Now, build-up in the practice is very important, occurs in any scattering material, including air, including water, including metals, and it is an additional factor, and this factor is more than one, which should be put in front of the exponential attenuation. As said, important to remember, the real conditions are not of good geometry. Build-up can add a significant dose rate. So if we are considering a calculation, a specific gamma calculation, we have to take into account the effect of build-up, especially in high Z materials, because although build-ups takes place in any material, including air, it is more likely to happen and to have a significant impact in those materials which are more massive, have a higher Z. However, as I mentioned, the linear attenuation coefficient depends not only on the energy, but also on the characteristic of the material. Therefore, a mass attenuation coefficient is also defined. The mass attenuation coefficient is defined as the ratio between the linear attenuation coefficient and the density of the material, because in the practice, the density of a specific absorber is an important parameter in determining the interaction of photons. In the practice, it is the mass attenuation coefficient which is used, so let's try to understand what this means. It means basically that the thickness of the absorber, you remember in the attenuation equation, It was E multiplied mu by T, by the thickness. So if we divide mu by rho, by the density of the material, well, we have to multiply T by rho again. This is called mass thickness. And the reason why I'm introducing this, it's because it is the standard way to indicate an attenuation thickness. We will not say that the shielding is 2 centimeters or 2 millimeters. We would say that the attenuation is, for example, 80 milligrams per centimeter square. So the unit in which we are expressing this thickness is a mass divided an area. Imagine to multiply rho, which is a density, so a mass over volume, by T, which is a thickness, so a length. The result is a mass over an area. Now, although this seems a little bit far from our experience, it is not. It is not. This way of expressing the mass attenuation coefficient is very popular in the practice in radiation protection and attenuation, but also in our offices. If you look at paper thickness is not indicated in microns or fractions of millimeters. Look at the paper of the photocopy machine. The paper thickness is indicated in terms of milligrams over centimeter square or grams over meter square. Like, for example, as I mentioned, the photocopy paper is 80 milligrams per centimeter square. And a number which is below that number is a very thin paper, but the number which is above approaches a cardboard or a very thick carton. So it is quite useful, and it is used also in the practice to express thicknesses in terms of mass thicknesses and not of real thicknesses. To wrap up, interactions of photons with materials are basically due to 3 phenomena: photoelectric effect, stripping an electron; Compton interaction, deflection of the photon and deposition of energy into a Compton electron; and pair creation. These mechanisms are also relevant whenever we do spectroscopy of gamma emissions. But for us, in the practical aspects of radiation protection, it's very important to remember that attenuation follows an exponential, ideally. In the practice, there is a build-up to consider, and this build-up depends on the material and on the energy of the radiation. We come now to neutrons, which, as you will see, are very different from other radiation in their interaction with matter. Charged particles interact by generating secondary electrons. Photons interact with atoms, generating again secondary electrons, which lose their energy in much the same way as beta particles. But neutrons, they can directly interact with nuclei. Neutrons, they carry no charge, so they don't interact via Coulombian forces. Moreover, they can directly create reactions in the nucleus by picking up a proton or more than one, or protons and neutrons, by being absorbed by the nuclei. So they have a more intimate way of generating an effect in a nuclide. Similarly to photons, nothing happens to neutrons between one interaction and the next one. Here I say that they can travel a lot, even centimeters, in a material without having any interaction, which means that if we, for example, choose a wrong detector, a wrong material to detect neutrons, there is even the possibility that that detector will be completely useless and neutrons will be completely invisible to that detector. What neutrons do in the interaction with nuclei is to generate heavy charged particles. They can come either from a nuclear reaction within the atom. So, for example, if a proton is emitted, is kicked out of the nucleus by effect of a reaction induced by a neutron, this would be a highly energetic proton which will interact with the surrounding materials a bit like an alpha particle will do. Or they can be the nuclei themselves, because nuclei can gain energy, kinetic energy, as a result of the collision with an incoming neutron. So very, very different way of interacting between neutrons and other, even uncharged particles. When we try to describe what neutrons do when they interact with materials, there is quite an important divide between highly energetic neutrons and low energy neutrons. These are normally called fast neutrons and slow neutrons or thermal neutrons. Sometimes, especially in nuclear physics, you will hear also about another category in between, which is called epithermal neutrons. But for us in radiation protection, given the big divide also in the way you can detect them, we speak about fast neutrons and slow neutrons or thermal neutrons. And what is the point, the dividing line? The dividing line is traditionally the so-called cadmium cutoff at 0.5 electron volt, which is the energy at which the interaction probability with the absorber cadmium changes abruptly. So normally the difference between high energy or low energy neutrons is determined by this cutoff at 0.5 electron volt. How slow neutrons interact with materials? Well, in most cases, the interactions include elastic scattering and also a large number of neutron-induced nuclear reactions, including, most importantly, capture of a neutron. So, when a slow neutron interacts with materials, it can generate a range of nuclear reactions, but certainly one of the most important is the capture of the neutron itself, normally accompanied, in this notation indicated by N gamma, accompanied by the emission of a gamma ray, a capture gamma ray. You can see here the attenuation curve for slow neutron in a specific material. This is plutonium-239. The probability of the N gamma reaction in this specific radionuclide is very high at low energies, decreases with increasing energies, and at certain point it has also a very complex, a very dramatic change in behavior. Now, for radiation protection purposes, we don't need to go into the details of describing this. Just appreciate that the probability of this interaction decreases almost linearly with increasing velocity, with increasing energy of the neutron. Therefore, low energy neutrons, they have a higher probability, this is a log scale, so much higher probability of generating the N gamma absorption reaction in this material. Fast neutrons, they can create a completely different range of effects, including knocking, directly picking up protons and neutrons and other aggregates from nuclei. But the probability of most neutron-induced reactions with increasing neutron energy drops off very rapidly. At higher energies, specific reactions take place, and they normally have a threshold. So a reaction like a specific NP, the reaction in which the neutron is absorbed and the proton is emitted instead, will happen only after a specific energy threshold. Under that energy, the probability will be very low. Another characteristic is the importance of scattering. Neutrons, fast neutrons, can transfer a lot of energy in one single collision, and as you can imagine, the result of this collision is also a recoil nuclei. And what is the most effective material to slow down, to attenuate neutrons, is a material which contains a lot of hydrogen. Because, as you remember, neutrons and protons, they have more or less the same mass. Therefore, the classical interaction of a neutron incoming over a proton will deliver the highest kinetic energy in any other interaction possible. Therefore, choosing a hydrogenated material means to enhance the probability to reduce energy and speed of neutrons. And normally, you may also know that absorbers and moderators are composed mainly of hydrogenated materials, paraffins, waters, very, very light materials. Very similarly to gamma rays, a narrow beam of neutrons behaves in the same way. So the intensity of the beam decreases exponentially with the thickness of the absorber, and the parameter, the attenuation coefficient, let's say, it's called macroscopic cross-section. You may hear about these words, microscopic and macroscopic cross-sections. These are probabilities of interactions which include the probability of scattering, the probability of absorption, the probability of capture, and many other nuclear reactions. Later on, we will define what is a cross-section, microscopic, small sigma, and macroscopic, capital sigma, which are very much used in neutron interaction calculations. But by now, this is the end of this section, and let's wrap up the neutron part. Neutron interactions are very, very different from other interactions, and they can be split into the two big categories of fast neutrons and slow neutrons. The result of a neutron interaction is a recoiling nuclei in most cases, if not a heavy charged particle being emitted by the nuclear reaction. For slow neutrons, we have seen that the probability of attenuation and interaction decreases with increasing energy, and the highly probable reaction is capture, neutron being captured and a gamma ray being emitted in this process, radiative capture and gamma. For high energy, so fast neutrons, other reactions can occur, and these reactions normally are characterized by a specific threshold. So they simply don't happen if the energy of the neutron is not high enough. Slowing down highly energetic neutrons is made very effectively by hydrogenated material, because the interaction with a recoiling nuclei, which maximizes the transfer of kinetic energy, is the interaction with a proton. So ideally, the ideal moderator or the ideal absorber for neutrons is composed of a lot of hydrogen. Shielding and attenuation of neutrons is quite complex, and normally it is done by specialized software, normally very complex in use and also in their understanding. This concludes this section related to interactions of radiation with matter. Important points to remember, this was just a review section, is that different radiation have different mechanisms of interaction with materials, and these different mechanisms deliver energy in different ways and intensity. We have, for example, appreciated that gamma radiation can interact via photoelectric effect, via Compton scattering, via pair creation, as an example. We have seen that neutrons have very complex and different ways of interaction, including nuclear reactions like pickup, absorption, and others. So to describe the way radiation interacts with materials, we need to know which radiation is interacting, what is the energy of that radiation, and in turn, what is the mechanism of interaction itself. And we also need knowledge of the material the radiation is interacting with. We have seen, for example, for gamma emissions, interactions depend on the energy, but also on the atomic number, on the Z of that material. So knowledge of the material is key. And the same goes for neutrons. We have seen that a hydrogen-containing material is much more effective than a heavier Z material in shielding, absorbing, or moderating neutrons. This was a review section, but as you will see, the interaction of radiation with matter is one of the most important topics for radiation protection, because the energy delivered during the interaction is the source for biological damage, and this is the focus for radiation protection.